After watching this lecture, students will be able to define what a colligative property is, as well as calculate freezing point and boiling point changes associated with colligative properties. So colligative properties are properties that depend on the concentration of solute particles that are in a solution without regard to their identity. So we'll be focusing on the number of particles present for all of our calculations. Now, your freezing point depression and boiling point elevation are the two colligative properties that we're going to focus on and do work with in this lecture. Okay, so freezing point depression is basically something that we see when we have a solution. So let's say like salt water versus just pure water. If we put both of those out at the same temperature, the water alone would freeze at a higher temperature than the solution of salt water. Okay, and we also see boiling point elevation in situations like engine coolant, when we use antifreeze and water and we mix them together and put them into our radiators, there is a slight increase in the boiling point of that solution, which allows for cooling to more efficiently happen in your engine that you have in your car. So freezing point depression and boiling point elevation are both colligative properties, and we're going to go ahead and look at these more intently. So let's talk about how the freezing point depression and boiling point elevation actually kind of occur. So when you have a solvent that's absolutely pure, you're going to have attractive forces between the particles as you start to cool down the temperature. And so those attractive forces are going to be stronger and stronger. The molecules are going to orient and eventually you freeze. However, when you introduce impurities, such as a solute, into that solvent mixture, what ends up happening is the solute particles actually get in the way of those interactions. And what ends up happening is that the molecules, the solvent molecules, have a harder time orienting and basically stabilizing to form, the frozen solid. So basically, the solute particles act as an interrupter to those attractive forces and subsequently require additional cooling in order for the solid to actually form. Now, boiling point elevation, as we see here, we have just pure solvent. Notice all the surface particles are all exactly the same molecule. So when they vaporize and go into their vapor form from the liquid form, there's nothing impeding that. But when you introduce a solute, notice that some of the particles are going to be solute, and then a mixture of solute and solvent along the surface. And what happens there is basically you just have less of the solute, less of the solvent at the surface, and you subsequently get less vaporization. So in order to get this to boil and reach the equilibrium point, what you end up with is basically a need for additional heat addition. So another thing I want to point out here, guys, notice we're talking about non-volatile solutes. This is something that will come up in some of your homework questions. Basically, a non-volatile solute is anything that's not going to vaporize in this process. So the solutes are going to stay in the solution. Okay, but basically, this is these are some of the driving forces or some of the considerations to think about when you're talking about freezing point depression or boiling point elevation. All right, so this brings us to our calculations. Okay, so our change in temperature associated with our freezing point depression or boiling point elevation are both going to be represented by this equation. So delta T is going to be the change in temperature, K is going to be a constant, M is your molality, and I is your Hoff Factor, which indicates the number of particles. Okay, so this constant will be provided to you. The constant is going to be different depending on if you're dealing with boiling point elevation or freezing point depression. Okay, but let's go ahead and talk about the Hoff Factor in a little bit more detail. So if you recall, the definition of colligative properties are basically properties that depend on the concentration of your solute particles, and not necessarily their identity, but basically how many particles are going to end up in solution. Okay, and so that directly connects to the Hoff Factor. Basically, that's the number of particles that a specific substance will put into solution. Okay, so non-electrolytes, or those covalent compounds that we talked about a few lectures ago, are going to remain intact when dissolved. So basically that molecular solvation, we talked about the sugar being surrounded by the water molecules, but it's not going to break into ions. It's going to stay as a single unit. Okay, so in that case, you're going to have a Hoff factor equal to 1. So your I value for covalent compounds is going to be 1. Now, if we have electrolytes or ionic compounds, basically those ionic compounds, when you put them in water, they break into their ion pieces. Okay, and so depending on the structure of your ionic compound, that's going to dictate how many particles it puts into solution. Okay, so if we look at this example here, we have NaCl. We know that it consists of Na plus and Cl minus. That's 1, 2 ions, so I is going to be equal to 2. If we look at this example, we have Ba2 plus 2 Cl minuses. Okay, so my I value there will be 3. Okay, here we have Na plus and NO3 minus. Okay, so your I here is going to be 2 again. Okay, and then if we look at this example, we're going to have 3 Ca2 pluses plus 2 PO4 3 minuses. Okay, and my I value here will equal 5. Okay, so basically your Hoff factor is going to be directly related to how many particles you put into solution. If you're ionic, you break it up into its ions and figure out how many ions are put into solution, and that gives you your I. Or if you're a covalent compound or non-electrolyte, I is always going to be 1. So let's go ahead and let's look at some practice problems here. So basically they are asking us at what temperature will a solution that is composed of 0.73 moles of glucose and 225 grams of phenol boil. The boiling point constant is 3.60 degrees C kilograms per mole. Okay, so guys, basically they're asking us what the boiling point of this solution is going to be, given that we've dissolved glucose in the phenol. Okay, so the first thing we need to look at is the fact that we're going to be looking at a colligative property problem. Okay, this delta T is going to be the change in temperature relative to the boiling point of the solvent. Okay, so we know that this is my solvent. Okay, and we know that this is my solute, right? So what we're then going to do is calculate our delta T, right? And because it's boiling point elevation, we're going to add that value to the boiling point of phenol. Boiling point of phenol is 181.7 degrees C. Okay, so, all right. So in order to get our change in temperature, we need to look at the variables we have. So first of all, K, okay, we've been provided. So we have 3.60 degrees C. Kilograms per mole. Okay, we've been provided the information we need to calculate our molality. Okay, we have our number of moles of solute and we have our grams of phenol. Okay, so what we're going to do there is we're going to take our 0.73 moles of our glucose and we're going to divide by 0.225 kilograms of our phenol. Okay, and then we need our I value. Now remember, our I value is going to be determined by how our solute behaves in solution. So glucose, a sugar, is going to be a covalent molecule, and we know that covalent molecules don't break up. So our I value here is going to equal 1. Okay, so we've plugged all these into our equation, and now we're going to calculate the numerical value associated with our delta T. And that's going to give us 11.68. If we check our units, we end up with degrees C. Okay, and of course we got our 2 sig figs, so we'll mark that. Okay, now this is the change in temperature. So this is how much the boiling point of the solution is going to increase versus the phenol alone. Okay, now they're asking at what temperature will the solution boil. Okay, so basically what we now need to do is we need to take our 181.7 degrees C, which is our boiling point of our solvent, okay, and we're going to add that to our delta T value, and that's going to give us 193.38 degrees C. 0 places past decimal, so 193 degrees C will be our boiling point of our solution. Okay, so notice our boiling point of the solution is higher than the boiling point of the solvent alone. Okay, so that's boiling point elevation calculations. So let's go ahead and let's do a freezing point calculation down here. So if we look at this, I want you to find the freezing point of a saturated solution of NaCl containing 28 grams of NaCl in 100 mils of water. And they've provided us with the freezing point constant, which we will use as our K value. Okay, so this is going to be a delta T equals KMI problem. Okay, so we have K. Okay, we can figure out I. We can also figure out M. Okay, so let's go ahead and let's take care of M really quick. Because M is going to require some additional work. First of all, our solute is NaCl. So we're going to take 28 grams of NaCl, and we have to convert this into moles. Okay, so we need to use the molar mass of NaCl. Then if we go ahead and we plug this into our calculator, we get 0.47909 moles of NaCl. Okay. And then we're going to take this value and we need to divide it by our by our mass in kilograms of our solvent. So we have 100 milliliters. Okay, we first need to convert that to grams. We know the density of our water. Okay, so 1 gram per milliliter. And then we want to be in kilograms. So there's 1,000 grams in 1 kilogram. Okay, and that's going to give 0.100 kilograms. Okay, and then we're going to take this value and this value and divide them to calculate for our molality. But we'll do that within the confines of the delta T equation. So delta T equals 1.86 degrees C kilograms per mole times M, which is 0.47909 moles per 0.100 kilograms times I, which because this is NaCl breaks into Na plus and Cl minus, so I is going to be equal to 2. Okay, so we plug that all in, and that's going to give us 17.822 degrees C. Okay, and if we look at our sig figs, we'll mark 2 there. Now, this is freezing point depression, right? So we know the freezing point of water is 0 degrees C, and we're going to be subtracting out our 17.822, okay, and that's going to give us negative 17 degrees C. Okay, and that's now our freezing point of our salt solution. So basically the calculations are pretty similar in terms of approach. The main thing is just making sure that you're plugging in the correct constants when you're dealing with them. Make sure that you're using the freezing point constant when you're doing calculations for freezing point, and that you use the boiling point constants when plugging those in, and subsequently you should be good.